This is page 17 in your note packet. What we have here, starting off, we're talking about similar shapes again, something that we've already talked about. And on the top of the paper, we have two similar shapes. This triangle and this one are similar. It says so right in the directions. And we're going to answer a few simple questions about it. First question is finding the scale factor. Now, if you don't remember how to find the scale factor, we're going to take one of the measurements in the first triangle, it doesn't matter which, and one of the measurements from the second triangle that corresponds. So it's got to be a corresponding measurement. So you could compare the 5 here with the 15, or you could compare the 13 with the 39, or the 12 with the 36. And we're answering question number 1 here. What is the scale factor? And it does give us an order. It says from triangle A to triangle B, so we got to match that order. So we're going to take a measurement from this triangle. I'll do this with the 5 and 15. And since it tells me triangle A to triangle B, I'm going to take the measurement from triangle A, in my case 5, and put it over as a fraction over the 15 from triangle B. Then I want to reduce that fraction. And when you reduce that, you'll get the scale factor. You could get the same scale factor by comparing the 13 to 39 or the 12 to 36. But since it does give us an order, the measurement from triangle A, this one, has to be first or on the top of your fraction. So now we have a fraction like this one, and you have to reduce it to find the scale factor. If you have trouble with reducing, remember the black calculator. If you have that, you can just simply type this fraction in using the fraction symbol above the 7 and hit enter. It'll reduce it for you. If you have other troubles, there's other resources. You should be able to reduce a fraction, but if you're having trouble, here's another resource or two. I just went on Google and typed in fraction reducer, and one of the first hits I get is this fraction reducing calculator. You scroll down, you can find this one. It says free-online-calculator-use.com/fraction reducer. And you can actually type in a fraction here. Now, this isn't the right fraction for this problem, but you can type in a fraction here. So I did 4/8 and asked it to reduce the fraction. It'll give me the answer here. It'll reduce the fraction for me. So you can use this if you really need to. I hope you can reduce a fraction on your own, but if not, there you go. Okay, for questions 2 and 3, you are simply going to calculate the perimeters for both of these triangles. Find the perimeter for triangle A, find the perimeter for triangle B. If you've forgotten perimeter, that's what you get when you add up all the sides around the outside of the shape. Don't count measurements inside. There aren't any in this case anyway. And then you're going to find the ratio of the perimeters of triangle A to triangle B. So you're going to do the same thing you did in problem number 1, except you're going to do it with the perimeters. The perimeter of this triangle compared to the perimeter of that triangle, triangle A, divided by the perimeter of triangle B, and reduce that fraction. It should be comparable to your answer to problem number 1. Now, your answers to problems 1 and 4 should be related to each other, we'll say, and predictably so. You get an answer that makes sense for both of those. But when we get down here to problems 5 and 6 and 7, our answer takes a little more thought for it to make sense. For problems 5 and 6, you're just going to find the area of the two triangles. To find the area of the triangles, remember, you're just going to do, since it's a triangle, 1/2 times base times height for both of them. The first one, half of 5 times 12, and the second one, half of 15 times 36. But when you compare the areas, you're not going to get the same results as you got in problems 1 and 4. You're going to get a different number, but it does make sense as to why you get a larger number. Your number is going to be not simply a ratio of 1 to 3, but 1 to 9. Our scale factor got a lot bigger. And here's why. Here's how we calculate the area for each of them. 1/2 times 5 times 12, 1/2 times 15 times 36. But to get from the 5 to the 15, we got 3 times bigger. It's being multiplied by 3. And to get from the 12 to the 36, it's also 3 times bigger. So our area gets multiplied by 3 and then by 3 again. When we talk about area of similar shapes, our scale factor is squared. 1/3 squared becomes 1/9. That's why we get such a different result for the areas when our triangles are similar. But if one shape is 5 times bigger, then its area is going to be 25 times bigger. If a shape is 10 times bigger than another one, its area is going to be 100 times bigger. We have to square the scale factor when we talk about area. On page 18, I'm going to ask you to use that information. So for the first question here on page 18, it says we've got two similar shapes. Notice there's no picture. If you'd like to, if you feel like you need it, then just quickly draw a sketch or a picture that you can use. So here I got a quick sketch. Here's two pentagons. Scale factor is 2 to 5. So that means any measurement in this triangle, in this pentagon, if I want to find the corresponding measurement in the other one, I'll multiply it by this scale factor. So if I had a measurement in the little triangle like this 2, and I want to find a measurement in the big triangle that corresponds to it, I would multiply the 2 times the scale factor to get the measurement in the big one. Now, if you remember, it makes a difference which scale factor, which number you put on top or bottom of the scale factor. We have our small shape and our big shape. And if you have a measurement in the small shape and you're trying to find the corresponding measurement in the larger shape, you multiply by the scale factor and put the larger number on top. If instead I had a measurement in the large one and want a measurement in the small one, I put the smaller number on top. For example, if I know this measurement in the small one is 10, and I want the corresponding measurement in the large one, I'm going to take the 10 and multiply by the scale factor. So here, I'm multiplying 10 by the scale factor. But if I multiply by 2 over 5, I'm going to get a little tiny measurement. I'm just going to get 4 for the value for x. That doesn't make sense. That's too small. This is the bigger one over here. I should be getting a larger number. If that happens, then my scale factor must be upside down. Instead of multiplying by 2 over 5, I want to multiply by 5 over 2. Here, if I multiply by 5 over 2, I should get 25 for my missing measurement in the larger pentagon. And that makes sense. That's about what that should be. All right, so that's a little recap. Now let's use this to answer our questions. What's the ratio of the perimeters for the pentagons? Well, as we learned on the other side of the paper, the ratio for the perimeters should be the same. We should still have 2 over 5. But when we get to question B, what's the ratio of the areas? It's not going to be 2 over 5. It's going to be 2 over 5 squared. We have to square this. Now, this is a little bit weird, but 2 over 5 squared is really simple to actually calculate. What we're simply going to do is square both the numbers. 2 squared is going to turn into 4. 5 squared is going to turn into 25. So our scale factor for the areas of these pentagons is 4 over 25 instead of 2 over 5. Now, starting at problem C, I'm going to ask you to use the scale factor to calculate the perimeter. But we basically do the same thing. The perimeter of the small one is 12. We want to find the perimeter of the large one. Simply multiply by the appropriate scale factor. Make sure you're doing it right, because the measurement I'm giving you is for the small one, so your result should be a larger number than the 12. When you get down to problem D, same idea, but now we're talking about area. So in the area, we're going to take the area of the small one, 20, and multiply it not by the scale factor, not 5 over 2, but by the scale factor squared, which will be 25 over 4. And that'll give us the area of the larger pentagon. Just so you know if you're doing it right, correct answer for problem number C should be right around like 30. The correct answer for problem D should be more than 100, maybe 120 something. All right, for the last problem on this assignment, problem number 9, you can follow these directions. The actual problem's up here. It says the ratio of the sides of a triangle is 4 to 5 to 7. The perimeter is 76 inches. What are the lengths of the sides? But the steps on how to do it are right here. Draw yourself a triangle, label the sides 4x, 5x, and 7x. This problem should look familiar. It was on our first test this semester. But I think people may have trouble writing down the equation for perimeter, so I'm going to help you out a little bit here. So here we drew a triangle, labeled the sides 4x, 5x, and 7x. An equation for the perimeter, well, 4x plus 5x plus 7x has to add up to the whole perimeter. So this plus this plus this has to equal the 76. You have a simple equation. You're going to combine like terms and solve for x. When you do that, you're going to get a decimal. It's going to be 4 points. When you do that, then the last step here is we're going to plug that back in. So this answer that you get for x here, you're going to plug it back in and do 4 times that number, 5 times that number, and 7 times that number. If you do that right, one of them comes out to a nice number, and 3 of them, the other 2 come out to a decimal. But that will tell us the actual lengths of these sides. If you want to check to see if you have it right, take your 3 side lengths, add them up. They should add back up to 76. And that's it for the first assignment for our e-learning days. You should now have pages 1 through 18 in your note packet completed.